Good. So let's get into where we left off last time. We're talking about numerical solutions. So I think I had just a couple of things left here from last time. Remember, actually, let me just flip down here. We'll just go through our summary. So remember, for numerical solutions, what we're trying to do is take these problems that we couldn't necessarily solve analytically, or if they don't have some closed form solution or analytical expression that goes with them. They're maybe more difficult, or there's some discontinuity, or there's some complexity that makes it difficult to solve. So what we can do instead is discretize our domain into a bunch of little bits and then model the heat transfer between those chunks as simple resistance equations. Right? This is an algebraic approach to the heat transfer problem. So we discretize the domain into some n control volumes. We perform an energy balance on each one. Again, trying to draw everything coming in because it just simplifies the approach a little bit. It makes it easier to remember what to do. So draw everything coming in, represent heat flows using a resistance model, solve the algebraic equations, and then verify the solution. So I think we kind of got to maybe step 3/3 to 4. I guess we'll pick up and just look at this system of algebraic equations and what that means and how you solve it. All right. So flipping back up here, this 1D numerical solution example, we've developed our set of equations. We have n equations, n unknowns. Our n unknowns are the temperatures at each node. We're trying to solve for the temperature of each node. We have energy balance equations that go with all those nodes, so you should have the same number. So what effectively you have, let me just write this out. So we have n equations, and we have n unknowns. Right? The equations are energy balance on each node. And the n unknowns are temperature, right? So T sub I, where I is in the set from 1 to n. So what you end up with is this basically big linear algebra problem. Right? These are algebraic equations. So what you have is this. You have this matrix A. It's a 2D matrix times some vector x. Right? Actually, for our problem, that's T. But just in general notation. And that's equal to some vector b, right? So remember your linear algebra solutions. This is what we have to solve. To solve this, we basically have to invert the A matrix, right? And there's a bunch of ways to do this. You could manually do that. You could do Gauss elimination. You could use MATLAB to solve or invert the matrix. You can use ease, right? Ease is basically just a matrix inversion tool. What it looks like, though, is let's actually write out for our example, what this all looks like. So let's say over here, we've got this big A matrix. What are the components of the A matrix? So if we look back up at, I don't know, let me slide back up here a little bit. So let's look at this equation here on the top. This equation here has a bunch of stuff multiplying the temperatures. So if I went through and I say collected everything that's multiplying T1, right? That's going to be K AC over delta X times -1. All of that is a coefficient in this matrix, right? For this one, it's the first equation, let's say, and it is stuff going with the first temperature. So it's right in the upper left corner of our matrix. For T2, it's going to be again in the first row, but T2 here is being multiplied by this stuff as well. So that's going to appear in our matrix. And then you have some other stuff that doesn't relate to either the independent variable or it doesn't relate to the temperatures, right? You have this G dot triple prime delta X over that stuff over there, right? So all that stuff is going to be a constant. This is like the B part of that equation. So what it looks like when you actually write it out, if we just sort of picked some general conduction problem, we'd have this first row. The first row corresponds with the first equation. So coefficient 1 would be K, let's say K times AS over delta X. The second coefficient would be k times as over delta x, right? So that stuff, oh, sorry, this should be minus, right, minus. So that first upper left is what's multiplying T1. Second is what's multiplying T2 in our first equation. Then there's nothing else. There's no other temperatures that appear on the left node. So then there's like a bunch of zeros, right? 0, 0, 0. So then you have a second equation. That second equation is your control volume on node 2. And on node 2, you have like slightly different things happening. So stuff multiplying T1 for equation 2, Kas over delta x. Then we have stuff multiplying T2 in our second one. That's going to be minus 2 Kas over delta x. Then you have, from the right-hand side on 2, you have 3. So you have Kas over delta x here. And then you have zeros. So what you end up with is this matrix is basically like a triangular matrix, right? You have stuff going like this, this, this. You have this sort of triangular sparse matrix that you have to invert. What's multiplying it? Over here we have in the first T1, then T2, dot, 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 down to Tn. And then that's equal to all the stuff on the right-hand side. So for, I think, the problem we were going through, it might look something like minus g dot triple prime at x1. Let's see, delta x over 2 times w times L. Then for row 2, it might be minus g dot triple prime x2, then delta x wl, right? So you can see that we're taking into account the volume that's changing, right? The nodes are slightly different. But basically, you just fill out this matrix and you have to invert it. So the solution to this ends up being, right, this all ends up being x, our temperature vector, is equal to A inverse times B. Right? And that gives you the solution. So like I said, there's many ways to do this. The way we're doing it in this class is using ease. And so all of this stuff, like, it's good to know it, because if, let's say, someday you're needing to do this and you don't have ease available, you need to know how to set it up. But we're just setting up a matrix and then inverting it. Questions on that? Yeah?
So I don't really remember much about linear algebra, but is it definitely in that order? Like, we have to multiply the A matrix times the B matrix?
Yeah, I mean, so when you are, the question was, is this the right order? Like, how do you know the order? So what you end up having to do is you say, I'm taking this expression over here, and the way it has to work is you have to like multiply first by A minus 1 over here, and then this, the order is important, right? So this moves over, this becomes A minus 1 here. So this, when you multiply it together, gives you the identity matrix, right? The identity matrix is just what do you call it? This vector of, or triangular diagonal vector of ones. When you multiply a diagonal vector in this matrix by another vector, it just gives back that original vector, which is temperature, right? Or x in this case. So yeah, it has to go this way for it to make sense. If you try to do it the other way, I think you end up with wrong dimensions in your result. Other questions on this? Okay. So that's, I think, the overview on 1D numerical. Let's talk about 2D numerical. I think you guys had a chance to do this in your discussion in radial coordinates, which is fun. But it might look something like this. This is in the notes if you want to look at it. Some things, sorry, before I go to 2D, what I want to point out here, this is the solution to the example. Let me just show you what I'm doing. So in ease, we have this generation function that's dependent on position x. So I wrote in ease this function. I just pass it a position x, and it evaluates g dot triple prime. So you might need to do something like this. If we wanted to replace this with some more complicated function that is a lookup table or something, you can do that, right? You just replace it. So then we set up the problem. Down here, we discretize. All right, so we're discretizing the domain into n nodes. We do that with a duplicate loop, as you now have learned. So duplicate takes the equation inside, and it takes the index that you're duplicating, and it replaces that index with the range that, with one of the values of the range that you specified. So basically, this duplicate loop is saying I've got n different x equations corresponding to this, where I takes the value of each index in that range. And so this is actually producing n equations in that duplicate loop. So that specifies x. Now down here, we have our energy balance, which is going off the page, but you can see I've formulated in terms of I minus 1, I plus 1. So this has to go from 2 to n minus 1. This will give you n minus 2 equations in e's. And then you fill in the remaining with, here's node 1, and then just off the screen is node n. And once you program all this in, you should be able to solve it. Okay. This is often the tricky part, right? Like, until you really get used to ease or get used to MATLAB or Python or however you're solving these, this part, the programming part, is the frustrating part. So if you find yourself stuck on this, office hours are a great resource. Piazza is a great resource. Don't post your code because I'll take it down. But do ask questions, right? Do ask questions. Okay.